let's look at a problem, problem 250 from our textbook. Let's solve this as an example of base excitation. Here I have a mass connected to a fixed support by a spring K, and the base is connected to the mass through a damper C, and I have a y base motion, x motion of the mass, and what's requested is to derive an expression for the force transmissibility. So I'll start first by deriving the equation of motion of this system. It's slightly different than the one we used for explaining the concept. Here I have a spring force Kx, motion's up, we have a compression, and then I have a damping force which is Cx dot minus y dot. So now the equation of motion based on Newtonian approach, we have negative Kx minus Cx dot minus y dot equals m times the acceleration x double dot. So now rearranging this equation, mx double dot plus cx dot plus kx equals cy dot. So it's basically the same as our previous derivation, except that we only have now one term for excitation. In the main derivation we had plus ky. So now I have only one term, which is cy dot, and defining y as amplitude y sine omega b t. Then the equation of motion becomes mx double dot plus cx dot plus kx equals c omega b y cosine omega b t. And normalizing the equation by dividing by m, x double dot plus 2 zeta omega n x dot plus omega n squared x equals c divided by m is already established as 2 zeta omega n omega b y times cosine omega b t. So now we only have one term for excitation, and this is the F0 of the excitation. So I can, we've already derived the expression x amplitude for one specific solution of the two we discussed earlier, which would be 2 zeta omega n omega b divided by the square root of omega n squared minus omega b squared all squared plus 2 zeta omega n omega b all squared, all times y. Now, an expression for the force transmissibility. First, the transmitted force, we've already established that the transmitted force is mx double dot, or negative mx double dot. And so in this case it will be I will amplitude y, 2 zeta omega n omega b square root of omega n squared minus omega b squared all squared plus 2 zeta omega n omega b all squared. This is x, capital X, the amplitude, times the cosine of omega bt minus phase angle theta. So that means x double dot is equal to omega b squared negative, the second derivative of the cosine, times y 2 zeta omega n omega b divided by the same square root omega n squared minus omega b squared squared plus 2 zeta omega n omega b whole squared. Now, multiplying this x double dot by negative m will give me the transmitted force F T is m times omega b squared y 2 zeta omega n omega b square root of 1 omega n squared minus omega b squared all squared plus 2 zeta omega n omega b all squared. And now we've established that m is equal to k divided by omega n squared. So we'll replace m by k divided by omega n squared omega b squared, and then I have y times the same expression omega b omega n squared minus omega b squared squared plus 2 zeta omega n omega b squared. Now the force transmissibility is Ft divided by Ky is. Now omega b over omega n, that's the frequency ratio r. I'll have r squared, and then dividing by omega n squared in the numerator and denominator, I'll have up here 2 zeta r divided by the square root of 1 minus r squared all squared plus 2 zeta r all squared, and this would be the new expression for the force transmissibility in this arrangement, when you have a string attached to a fixed base and we have another moving base on the bottom of the mass with a damper C.